let me just give you a quick 20-odd minute overview of PHENIX. And so just to remind people that PHENIX is this collaboration between multiple groups. So my group at Berkeley here, Tom's group at New Mexico and Consortium in Los Alamos, Matt Baker and Corey at Baylor, UT Health, University of Texas Health. Matt has very recently moved there from Baylor College of Medicine, so that's why those things don't match up. Randy Reed's group in Cambridge, and then Jane and David Richardson's group at Duke. And we all work on different parts of the structural biology problem. We originally started looking at crystallography, but as you can see, have expanded to other things. And I'll remind you later on, but there is a new publication that describes recent developments in PHENIX, which is a great paper to read. So this has been a collaboration for 20 years now, which is, arrived where we are in terms of the PHENIX program. And as many of us would tell you, this is a really great thing to do, this collaboration. It's been one of the great things we've worked on over the last 20 years. So when we started off developing PHENIX, it was really something for more automation in crystallography. And we started off building this open source library, this computational crystallography toolbox, and the PHENIX software. But over the years, there's all sorts of things that have developed around that. And I'm not going to talk about all of these, but just to say that electron microscopy was one of these, some of the early collaborations with Hua Chu's group at Baylor, who's now at Stanford. And that's going to be the main topic today, and tomorrow is the cryo-electron microscopy. So, one of the goals of PHENIX is to automate structure solution a bit more. It's great to go through the process of solving structures with cryo-EM or crystallography, but ultimately you want to understand the structure and get at the biology. So some automation is helpful. Something where we can have new programming concepts and new algorithms, and you'll hear about some of those today and tomorrow. Something which is easy for people to get into, but also allows more experienced users to do more challenging things and long-term development and support. And you may wonder why it's called PHENIX. It's called PHENIX because it's based around something called Python, which I can't imagine anybody's not heard of these days. When we started off, most people hadn't heard of Python. Now it's what everybody uses for a lot of things, including all sorts of machine learning and things like that. And the focus originally was on crystallography, as you can see, but that's really evolved over time. So Python is a key thing, and it makes it possible for us to rapidly develop software. There's a lot of crystallographic algorithms, which we're not going to talk about, but we'll get to in a later workshop. And because of things like Python, we can really develop and fix things in PHENIX quite quickly. So in the context of crystallography, this is how crystallography works on a good day in terms of all the steps you go through to solve a structure and finish a structure. So in PHENIX, we've developed over the years things that are designed to address these different steps. In terms of using PHENIX, for those of you that have used PHENIX, I think some of you may have used what's called the command line. If you open up a terminal window on any of the platforms where PHENIX runs, you can type commands and things will happen. So this is one way that you can use the program. And it's the way 20 years ago, most programs worked. Actually, a lot of programs worked. 20, 25 years ago, 30 years ago, you were just typing things at the command line. And there's nothing wrong with that. It's a great way to do things if you're writing scripts or you want to do something quickly. Great way to do things, very quick. And there's a lot of automation that actually happens even in running the programs this way. I suspect those of you that have used PHENIX more often though are using this graphical interface, which certainly looks nicer than the command line and is a way to present the tools to you. It's a way to present the information to help you set things up and to look at the results. And that's how we'll be doing things today. because it is a nice way to interact with the software. And I have to say, it's how I use PHENIX most of the time, is I use a graphical interface. One of the other things that we did with PHENIX was to integrate it with some of the other graphical tools. So COOT, for example, is originally a crystallographic model building program, is now used for electron microscopy as well. So there is a very nice integration there that we will probably see today in various places. There are also, there's an integration with PyMol. PyMol's not for model building, but makes great pictures. And we are working with the Chimera X developers to have a better integration with Chimera X as well as a tool for visualization that is more geared towards electron microscopy, and we're working hopefully to integrating some of the PHENIX tools so they can be used within Chimera X. But that's a work in progress. So even though crystallography has been around for a long time, 100+ years, there's still a lot of things that need to be done in crystallography, and this just highlights, I'm not going to go through these, but this just highlights some of the things we've done over the last few years to try and make solving crystal structures better. Some of these things here actually go beyond crystallography, but this is not the end. Actually, there's a lot of things still left to solve in crystallography. The first one is dealing with low resolution. This is a theme that I'll return to when we talk about electron microscopy. Completing structures in crystallography, if you have reasonable resolution, you can often arrive at a structure quite quickly, sometimes even at the beamline where you collect the data. But dealing with all of the complications, the identifying what the species is, recognizing ligands, metals, ions, waters, there's all sorts of things to think about. And there's things like disorder. At high enough resolution, you see disorder in your model, you see multiple conformations. So these are all things that actually often make it hard, or time consuming to get to a final model. So that's one challenge in crystallography that is still not dealt with automatically, and actually is going to be a challenge in cryo-electron microscopy as well. And then refinement of models in crystallography certainly is not fully automated. There's a lot of decisions that need to be made. There are things that happen in crystallography that make life challenging, like twinning. And then ultimately, crystallography is really a technique that's about chemistry. You're trying to understand a protein structure, but that's really chemistry. And that is one of the places it's hard to automate things, but it's one of the things that is most important in the process. And we can make the same statement about electron microscopy as well. If you're trying to use that to solve the structure of a protein, you really are dealing with chemistry ultimately. So that's a very quick summary of PHENIX and some of the crystallographic aspects. I wanted to quickly now just talk about cryo-electron microscopy. So thinking back 15 years, so about 2005, this is kind of the state of cryo-electron microscopy. It was applied to many large systems, was limited to larger systems. These are some pictures here from the National Center for Macromolecular Imaging. And, you know, some great examples of looking at viral proteins, looking at these large complexes, and being able to see that electron microscopy results were similar to crystallographic results at the same resolution. So very important, but a little bit constrained in terms of what it could do. A few years later, Steve Ludker, Hua Chu, and colleagues, and Matt Baker was actually involved in some of this work, I'm pretty sure, showed that they could get to resolutions that, you know, you could call high resolution compared to the state of the art. And so at, say, 4.5, 5 angstrom resolution, it was possible to even build models automatically. So this was pretty amazing work about 10 years ago. And so this is a slide that I made a long time ago, actually, for a course that I teach. And I said in this slide that combining cryo-EM and crystallography is going to be a powerful technique. So I was kind of right, and that was true for a while. But just a few years later, people showed in these very high symmetry viruses that they could get to similar resolutions in crystallography and cryo-EM, and really then start to think about not automatically, but using crystallographic tools, model building tools by hand to build structures into cryo-EM maps ab initio. And this just shows you some of the features here that look very similar between the crystallographic and cryo-EM maps. So that was a great step forward as well. A few years later than that, new detectors for electron microscopes were developed. And the great thing about these detectors, it made it possible to correct for sample drift during imaging. So, and I'm not sure how well this will come out in Zoom, but there's a big difference between a normal non-drift corrected image and the drift corrected image. The resolution is visibly different. And that has been transformative for cryo-EM. So that a year later, it was demonstrated could get to resolutions that were very comparable to crystallography at about 3 angstrom resolution. A couple of years later, people showed that you could get to resolutions that were more typical for crystallography, the 2 angstrom kind of range, and see things like ligands in proteins. And even more recently, so this is some work from last year, I think, showing apoferritin at about 1.5 angstrom resolution. So very clear what's going on. And more recently, this is work from Shaw-Sherris and others, but there are other papers that have come out like this very recently, really demonstrating atomic resolution. So these are a 1.2 angstrom resolution, where that is what historically we define as atomic. We can see atoms. You can see these round things that look like atoms. And you can see things that look like hydrogen atoms even. So cryo-EM has really gone beyond being just something to supplement crystallography. It is something that is comparable actually to crystallography at pretty much all resolutions. Maybe not quite yet at the 0.6 angstrom resolution that crystallography can achieve, but very, very impressive and a very, very quick development in this field. I mean, amazingly fast, actually. So there is much excitement and a lot that's very promising about cryo-EM. However, I think it is also worth pointing out that these fantastic, very high resolution maps are not the norm. It would be great if they become the normal. That would be, we'd all be very happy if that were the case, because it would make all of our lives a lot easier. But if you look, this is a graph that I made here of by year, the number of, these are maps deposited, not structures necessarily, but maps deposited at different resolution ranges. And what you can see is that even in 2019, last year, the majority, the place where we have the largest number of maps, that is between 3 and 4 angstrom resolution. And that's actually growing. There is some increase in the 2 to 3 angstrom resolution range, which is great, but there are still a large number of maps deposited in the 4 to 5 angstrom range. So typically in cryo-electron microscopy, single particle cryo-electron microscopy, we are dealing with maps that are in this 3 to 4 angstrom resolution range. And that presents challenges. It presents challenges in crystallography actually as well. This is a histogram of crystallographic structure resolutions. And so you can see that typical resolutions for crystallography are around 2 angstrom, but we have a significant fraction, say 7% in this 3 to 4 angstrom range. So this is a problem we've had to work with in crystallography. And it's really the same problems that we see in electron microscopy at the typical resolutions people are working at, which is, you know, if you're at 1 angstrom resolution, it's very clear what's going on. If you're at 4 angstrom resolution, it's very challenging to understand what this map, whether it's crystallographic or electron microscopy, what this is telling you. doesn't really tell you where the side chains are. Figuring out what this actually is, if this is an alpha helix, can be challenging. So for both crystallography and cryo-electron microscopy, we have this problem at lower resolution of how to interpret these maps. And this is one of the things that Tom will talk about today. And then how to make models that make sense. And that's one of the things that we'll talk about tomorrow in terms of refinement and validation. So that's a challenge, but one of the good things, okay, getting some questions, that's great. We'll get to those later. One of the good things is that once you've done the experiment to get to the initial or the sort of, let's say, the data, the process for both crystallography and cryo-EM has a lot in common. So in crystallography, once we get to our process diffraction data, and in cryo-EM, once we get to our reconstructions, so a three-dimensional reconstruction for the volume, the steps after that have a lot in common. There are details a little bit different, but there's a lot in common. In crystallography, we have to solve this phase problem because we don't collect the full set of information required to give us a three-dimensional reconstruction. So we have to solve this phase problem. So that is a challenge in crystallography, but there are ways to tackle that. We don't have that problem in cryo-EM because we get the phases in the experiment. So that's great. But after that, we have to go through a process of improving the map or the reconstruction. Once we've done that, we've got the best view of the object. Then we go through trying to build a model in one way or another. And then once we have that model, we have to go through refinement and validation of the model. And they involve dealing with things like ligands, which we'll talk about tomorrow. And once you've done that, there are places to deposit the models and the data in both cases. So the good thing is that a lot of the steps are the same, and it turns out that we can modify or expand on things developed in crystallography to develop tools for the cryo-EM case. Again, the details are different and things need to be changed, so it's not exactly the same, but the great thing for us within the PHENIX team was that we could leverage a lot of what we've done already to build tools for electron microscopy quite quickly. So this means there are a number of tools. This is not an exhaustive list, but these are some of the main things that are now available in PHENIX for electron microscopy. Getting symmetry from a map, improving a map through sharpening or density modification. So just to show you sharpening a map, you can go from a more blurry map to a more detailed map. With density modification, we can improve the map in a way that it makes it look more like what we know about macromolecules. And segmenting maps automatically, trying to fit models either through docking or automated building, then refining a model against a map, and then validating the model and the map. So we're going to hear about, today and tomorrow, we'll hear about map improvement, so sharpening and density modification, automated model building, which I'm sure Tom might talk about segmentation as part of that. And you'll hear about symmetry as well from the map. And then tomorrow we'll talk about the refinement and the validation. There are some other tools as well, but we don't have time to go through all of those. It might be a topic of a later workshop. So just as there are in crystallography, there are still challenges in cryo-EM. We developed some tools, but there's a lot of things. I'm not going to go through these, but just to say that, cryo-electron microscopy maps often have more variable resolution across the map than crystallographic maps. When we think about the kinds of structures we're looking at, these are can be large molecules, much larger than we've had to deal with in crystallography. Sometimes the starting models are quite a long way away from the answer because they might be homology models even. You might not even know exactly what is there in the map or in the volume. And then there are still questions about how to validate the models against these maps. And there are some open questions about validating the maps themselves. Okay, so I'll finish up and just say that, hopefully you all know that you can get PHENIX on the web. Go to the PHENIX website and download it. easy to get for academics. If you're in a company, let us know and we can talk. It's supported on the kind of platforms you're likely to use, like Mac, Windows, Linux. There's a lot of documentation actually as well, so it's a great place to start in terms of trying to get your questions answered. But if the documentation doesn't answer the questions, there's places you can email us and ask for help, report a bug if you think something's not working. And we release a new release, an official release, typically every 6 months for PHENIX. And in between, we release what's called nightly builds. So these are the latest development versions. If you want to get the latest thing, or we've told you we've fixed a bug that you told us about, you can go to the nightly builds and download those. And it's great that you're attending this workshop. We hope you get a lot out of it, but we have also put video tutorials online on YouTube. Certainly the younger people amongst you very much prefer looking at videos than reading things, which is great, perfectly understandable. You don't have to be young to look at these. You can be old too, or older, that's fine. So there's about 30 video tutorials. They're, tend to be around about 5 minutes each. So great place to look and get some introductory or some, in some cases, some detailed information about some of the things in PHENIX. Covers a range of topics. And this is something that Dorothy has spent a lot of time setting up. And we'll be adding more and more of these tutorials moving forward. So I'll finish and say thanks to all of the people that work on PHENIX. So there's all these folks on the left here involved in the PHENIX collaboration, the team, and all of the people here that do the work, and you'll hear from some of these folks today and tomorrow. But then just to acknowledge all of the people we've collaborated over the years and continue to collaborate with, and to thank the users, folks like you who use the program and give us feedback. We really like to get feedback. It helps us make the program better for everybody. And then funding, this PHENIX has been mainly funded by NIH, which we're very grateful for. But also we have an industrial consortium which helps fund the development of features for industry for PHENIX. So I'll finish and say thank you here, and just remind you that there's this new paper that is from last year that describes new tools in PHENIX for crystallography, both X-ray and neutron crystallography, and also cryo-electron microscopy. So do check this out if you haven't had a chance already. And if you're going to cite PHENIX in a publication, this is the thing to cite. I will actually stop sharing my screen. There were, I see a couple of maybe questions, which I'll very quickly get to in the chat window. So there was a question, I guess, is Cryo-EM, are Cryo-EM maps generally lower resolution? So currently I would say that is true, that if you looked at that distribution in crystallography, the sort of typical resolution for a crystallographic experiment is around about 2 angstrom resolution. And that is not the typical resolution in Cryo-EM. Currently, in single particle Cryo-EM, the typical resolution is more around between 3 and 4. Now, that's not an intrinsic limit of the experiment. It's, as people have shown, you can get to close to 1 angstrom resolution with electron microscopy. So it's not an intrinsic limit. It's probably a reflection of several things. It's a reflection of maybe sort of the order in the molecules. The great thing about Cryo-EM is you can look at molecules that are, very quickly frozen in solution, and they will exhibit some of the flexibility that the molecule has. So I think that's one of the reasons that reconstructions are often a bit at lower resolution these days. People are developing methods to try and improve that in multiple ways. Also, the technology is still being developed. The microscopes are still getting better. The detectors are getting better. There's things that are generally improving in terms of technology for the experiments. So it's likely that in general, electron microscopy may move to higher resolution in general, but I think we still have to see whether that becomes the same as crystallography. That's maybe unlikely, because crystallography selects for things that form ordered crystals. So the experiment itself tends to select for things that are more ordered. So I think that hopefully explains some of the reasons, but it's you know, it's still a work in progress. There is a long way that the Cryo-EM has to go, and that's a very exciting